Before there was light, before there was time, before there was even space to hold anything at all, there was a question that had not yet been asked. It is a question that would only emerge billions of years later inside the minds of curious beings on a small planet. That question is simple, yet it carries the weight of everything that exists. How did the universe begin? To understand this, we must imagine something that is almost impossible for the human mind to grasp. We must imagine nothing, not darkness, because darkness is something. Not emptiness, because emptiness still implies space. True nothingness means the absence of space, time, matter, energy, and even the laws that govern them. It is not a void. It is the absence of existence itself. Human beings are not naturally equipped to understand nothingness. Every thought we have depends on contrast and presence. Even when we close our eyes and try to picture darkness, we are still imagining a space where darkness exists. But the state before the universe was not darkness. There was no place for darkness to exist in. There was no time passing. There was no before and no after. The very idea of sequence did not exist. It is here that science meets the limits of imagination. Because when we talk about the beginning of the universe, we are not simply talking about the start of objects or events. We are talking about the origin of reality itself. For thousands of years, humans have tried to answer this mystery using stories, myths, and philosophies. Ancient civilizations looked at the sky and saw patterns, gods, and meanings woven into the stars. Some believed the universe was eternal, existing forever, without beginning or end. Others imagined it being created by powerful forces or divine beings. These ideas were attempts to make sense of existence using the tools available at the time. They were not scientific in the modern sense, but they reveal something important. The desire to understand where everything comes from is deeply rooted in human nature. As knowledge grew, so did our methods of investigation. Observation replaced speculation. Measurement replaced imagination. The invention of telescopes allowed us to see farther into the universe than ever before. With each discovery, the universe appeared larger, more complex, and more mysterious. Stars were no longer points of light. They were distant suns. Galaxies were not just patterns in the sky. They were vast systems containing billions of stars. And as scientists looked deeper into space, they also began to look back in time. Light travels at a finite speed. This means that when we observe distant objects, we are seeing them as they were in the past. A star that is 1,000 light years away appears to us as it was 1,000 years ago. A galaxy millions of light years away shows us an image from millions of years in the past. In this way, the universe itself becomes a kind of time machine. By looking farther into space, we are also looking further back toward the beginning. This realization changed everything. It suggested that the universe had a history, and if it had a history, it might also have a beginning. The turning point came when scientists began to notice something unusual about distant galaxies. They were moving away from us. not just a few, but almost all of them. And the farther away they were, the faster they seemed to be receding. This observation hinted at something profound. The universe was not static, it was expanding. Space itself was stretching, carrying galaxies along with it. This discovery reshaped our understanding of the cosmos. If the universe is expanding now, then in the past it must have been smaller, denser, and hotter. This leads to a powerful idea. If we trace this expansion backward far enough, everything in the universe would have been compressed into an extremely small, dense state. A state where the laws of physics as we know them begin to break down. This moment is often referred to as the beginning of the universe, not an explosion in space, but an expansion of space itself. It is a concept that challenges intuition. There was no center from which everything exploded. Instead, every point in space was part of the expansion. Every region of the universe was once closer together. But even this idea raises deeper questions. What caused the universe to begin expanding? Why does anything exist at all? These are questions that science continues to explore, and while many answers have been proposed, none are complete. What we do know is that the early universe was a place of extreme conditions. Temperatures were unimaginably high, energy was packed into a tiny volume, the familiar particles that make up atoms had not yet formed. It was a chaotic and dynamic environment, governed by physical laws that we are still trying to fully understand. At this earliest stage, the universe was not made of stars or galaxies. It was a sea of energy and fundamental particles interacting in complex ways. The forces that shape our world today, such as gravity and electromagnetism, were not yet distinct. They may have been unified into a single force. As the universe expanded and cooled, these forces began to separate, giving rise to the structure we see today. This process happened incredibly quickly, in fractions of a second, yet its consequences would shape the entire history of the cosmos. The idea that the universe had a beginning marked a major shift in human thought. For centuries, many believed the universe was eternal and unchanging. The concept of a beginning introduced the possibility that the universe evolves over time. It has a past, a present, and a future. This perspective allows us to study the universe as a dynamic system, one that changes and develops. It also connects us to the cosmos in a profound way. The atoms that make up our bodies were forged in the processes that followed the beginning of the universe. In a sense, we are part of that history. Despite all the progress we have made, the question of what came before the beginning remains one of the greatest mysteries in science. Some theories suggest that our universe may be just one of many, part of a larger multiverse. Others propose that time itself began at the moment of creation, making the idea of a before meaningless. There are even ideas that the universe could cycle through phases of expansion and contraction with no true beginning or end. Each of these possibilities pushes the boundaries of our understanding and challenges us to think beyond conventional limits. What makes this journey remarkable is not just the answers we find, but the questions we continue to ask. The search for the origin of the universe is not only a scientific pursuit, it is also a reflection of our desire to understand our place in existence. When we look up at the night sky, we are not just observing distant objects, we are witnessing the story of the universe unfolding. Every star, every galaxy, every beam of light carries information about the past. By studying them, we piece together the history of everything. The beginning of the universe is not just a moment in time, it is the foundation of all that exists. It set the stage for the formation of matter, the creation of stars, and eventually the emergence of life. Without that beginning, there would be no galaxies, no planets, and no observers to ask questions. This realization gives a new perspective on existence. It shows that the universe is not just a collection of objects, but a continuous process of change and evolution. As we continue this exploration, we move closer to understanding the first moments of existence. We examine the evidence left behind in the structure of the universe. We study the faint glow of ancient radiation that fills space. We analyze the distribution of galaxies and the behavior of cosmic expansion. Each piece of data brings us closer to the truth, yet also reveals new mysteries. The deeper we look, the more we realize how much remains unknown. In this chapter, we stand at the edge of knowledge, looking back toward the beginning. We confront the limits of imagination and the challenges of understanding something so vast and fundamental. The story of the universe is not just about distant events. It is about the origin of everything we know. It is about the transition from nothing to something, from simplicity to complexity, from chaos to structure. And so the journey begins here, not with answers, but with a question that has echoed through time and will continue to drive exploration for generations to come. How did the universe begin? In the beginning, there was no explosion in the way we commonly imagine it. There was no fireball expanding into empty space, no center from which everything burst outward. Instead, what occurred was something far more subtle and far more profound. The birth of the universe, known as the Big Bang, was the rapid expansion of space itself. Every point in the universe began to stretch away from every other point, not because they were moving through space, but because space itself was growing. This idea challenges our everyday understanding of motion and distance, but it lies at the heart of modern cosmology. To grasp this concept, imagine dots drawn on the surface of a balloon. As the balloon inflates, each dot moves away from the others. From the perspective of any single dot, it appears as though everything else is receding, yet there is no central point on the surface where the expansion begins. The surface itself is expanding. In a similar way, the universe expands in all directions at once. Every galaxy moves away from every other galaxy, not because they are flying through space, but because the fabric of space between them is stretching. This expansion did not begin gently. In its earliest moments, the universe underwent a period of extraordinarily rapid growth. Within a fraction of a second, it expanded from a size smaller than an atom to something vastly larger. This phase, often referred to as inflation, set the stage for everything that followed. It smoothed out irregularities, stretched tiny fluctuations, and created the large-scale structure of the cosmos. Without this rapid expansion, the universe we see today would look very different. At the very start of this expansion, The universe was unimaginably hot and dense. Temperatures were so extreme that the familiar building blocks of matter could not exist. There were no atoms, no nuclei, not even stable protons or neutrons. Instead, the universe was filled with a seething mixture of energy and elementary particles. These particles were constantly being created and destroyed in a chaotic dance governed by the laws of physics. It was a state unlike anything we experience in the present universe. As the universe expanded, it began to cool. This cooling was not a loss of heat to an external environment, because there was nothing outside the universe. Instead, it was a natural consequence of expansion. As space grew larger, energy became more spread out and temperatures dropped. This gradual cooling allowed the first stable particles to form. Quarks combined to form protons and neutrons. These particles would later become the building blocks of atomic nuclei. The earliest fractions of a second after the beginning are still not fully understood. The conditions were so extreme that our current theories of physics cannot fully describe them. Scientists are working to develop a unified framework that can explain how gravity behaves at such high energies, possibly through theories like quantum gravity. Until then, the very first instant remains one of the deepest mysteries in science. Yet, even without a complete understanding, we can reconstruct much of what happened shortly afterward. One of the most important developments in the early universe was the separation of fundamental forces. Today, we recognize four basic forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In the earliest moments, these forces may have been unified into a single force. As the universe cooled, they began to separate, each taking on its own role in shaping the cosmos. This process influenced how particles interacted and how structures eventually formed. Within the first few minutes, a critical event took place. Protons and neutrons began to combine to form the nuclei of simple elements. This process is known as nucleosynthesis. The universe at this stage was hot enough to allow nuclear reactions, but cool enough for nuclei to remain stable once formed. The result was the creation of the lightest elements, primarily hydrogen and helium, along with small amounts of lithium. These elements would later serve as the raw material for stars and galaxies. Even after nuclei formed, the universe was not yet transparent. It was filled with a dense fog of charged particles and radiation. Light could not travel freely because it was constantly scattered by electrons. The universe was opaque, similar to the interior of a star. It would take hundreds of thousands of years before conditions changed enough for light to move freely through space. When that moment finally came, it left behind a faint glow that still exists today, a relic of the early universe. The evidence for this origin story comes from multiple sources, each reinforcing the others. One of the strongest pieces of evidence is the observation of cosmic expansion. Distant galaxies are moving away from us, and their light is stretched to longer wavelengths, a phenomenon known as redshift. This observation supports the idea that space itself is expanding. The farther away a galaxy is, the faster it appears to be receding, which matches predictions from the Big Bang model. Another key piece of evidence is the abundance of light elements. The proportions of hydrogen and helium observed in the universe match the predictions of early nuclear synthesis. This consistency provides strong support for the idea that these elements were formed in the first few minutes after the beginning. It is a remarkable example of how theoretical calculations can be confirmed by observation. Perhaps the most compelling evidence is the presence of the cosmic microwave background radiation. This faint radiation fills all of space and represents the afterglow of the early universe. It is incredibly uniform, but contains tiny fluctuations that correspond to variations in density. These fluctuations would later grow into galaxies and clusters of galaxies. By studying this radiation, scientists can learn about the conditions of the universe when it was only a few 100,000 years old. The Big Bang was not just the beginning of matter and energy. It was also the beginning of time. According to our current understanding, time itself started at this moment. This means that asking what happened before the Big Bang may not have a meaningful answer. Without time, the concept of before does not exist. This idea is difficult to accept because our thinking is deeply rooted in the flow of time. Yet it highlights the uniqueness of the universe's origin. Despite its name, the Big Bang was not an explosion in space. It was the creation and expansion of space itself. There was no pre-existing stage on which it occurred. The universe did not expand into anything. Instead, it created its own space as it grew. Every point in the universe can be traced back to this initial state, making the Big Bang a universal origin rather than a localized event. As we piece together this story, we begin to see how the universe evolved from simplicity to complexity. What started as a hot, dense state of energy gradually transformed into a structured cosmos filled with galaxies, stars, and planets. Each stage of this evolution followed naturally from the laws of physics, yet the outcome is incredibly rich and diverse. It is a testament to the power of simple rules acting over vast spans of time. The study of the Big Bang is not just about understanding the past, it also helps us predict the future. The rate of expansion, the distribution of matter, and the properties of energy all influence how the universe will evolve. Will it continue to expand forever, growing colder and more diffuse? Will it slow down and eventually collapse? Or will something even more unexpected occur? These questions are still being explored, and each new discovery brings us closer to the answers. What makes this story so compelling is that it connects the smallest scales to the largest. The behavior of tiny particles in the early universe determines the structure of galaxies billions of years later. The laws that govern atoms also shape the evolution of the cosmos. This unity of physics across scales is one of the most beautiful aspects of science. It shows that the universe, despite its complexity, is governed by underlying principles that we can understand. As we continue to explore the origins of the universe, we are not just uncovering facts, we are building a narrative that explains how everything came to be. From the first moments of expansion to the formation of the first atoms, each step is part of a larger story. It is a story that spans billions of years and countless transformations. Yet, it all begins with a single event. The Big Bang represents the starting point of that journey. It marks the transition from nothingness to existence, from simplicity to structure, from possibility to reality. It is the moment when the universe began its long and complex evolution. And although much remains unknown, the progress we have made in understanding this event is one of the greatest achievements of human thought. In this chapter, we have taken a step closer to the beginning. We have explored how the universe expanded, how it cooled, and how the first particles and elements formed. We have seen how evidence from observations supports this picture and how it fits within the framework of modern physics. Yet this is only the beginning of the story. The early universe still holds many secrets, and the next stages of its evolution are just as fascinating. In the earliest instance after the birth of the universe, reality existed in a form so extreme that it defies ordinary understanding. Time had just begun. Space was rapidly expanding, and the temperature of the cosmos was beyond anything that can be recreated even in the most advanced laboratories. This was a universe not of stars or galaxies, but of pure energy, fluctuating fields, and elementary particles emerging and vanishing in fractions of a second. These first moments set the foundation for everything that would come later, shaping the structure and behavior of the universe in ways that still influence it today. To understand this period, we must look at intervals of time so small they are almost meaningless in human terms. Within the first tiny fraction of a second, far less than the blink of an eye, the universe underwent dramatic transformations. One of the most important of these was a phase known as cosmic inflation. During this period, the universe expanded at an extraordinary rate, growing exponentially in size in an incredibly short amount of time. What began as a region smaller than a subatomic particle expanded to a size that would eventually encompass the observable universe and beyond. This rapid expansion had profound consequences. It smoothed out irregularities and made the universe appear remarkably uniform on large scales. Without this smoothing effect, matter might have been distributed unevenly, leading to a chaotic and fragmented cosmos. Inflation also stretched tiny quantum fluctuations, minute variations in energy that exist at the smallest scales, into much larger structures. These fluctuations would later become the seeds of galaxies, clusters, and the vast cosmic web that defines the large-scale structure of the universe. At this stage, the universe was dominated by extreme temperatures and energies. The familiar distinctions between forces and particles did not yet exist in the way we understand them today. Instead, the fundamental forces may have been unified into a single force, a concept that physicists continue to explore through theories that attempt to combine all interactions into one framework. As the universe expanded and cooled, this symmetry began to break, and the forces separated, each taking on its own unique role. One of the first forces to emerge distinctly was gravity, which would later govern the motion of galaxies and the formation of large structures. Soon after, the strong nuclear force separated, binding quarks together to form protons and neutrons. The weak nuclear force and electromagnetism also became distinct, each influencing how particles interact and transform. This separation of forces is known as symmetry breaking, and it played a crucial role in shaping the behavior of matter. During these early moments, the universe was filled with a dense plasma of particles. Quarks, the fundamental building blocks of protons and neutrons, moved freely in a hot, energetic environment. They collided with each other constantly, forming and dissolving in a dynamic equilibrium. Gluons, the particles that carry the strong nuclear force, acted like invisible threads, binding quarks together under the right conditions. However, at such high temperatures, stable combinations could not yet persist for long. As the universe continued to cool, a critical transition occurred. Quarks began to combine more permanently, forming protons and neutrons in a process sometimes referred to as quark confinement. This marked the beginning of a new phase in the evolution of the universe. Instead of a chaotic sea of free quarks, the cosmos now contained more stable particles that could serve as the building blocks for atomic nuclei. At the same time, another important imbalance was taking shape. For reasons that are still not fully understood, there was a slight excess of matter over antimatter. In theory, matter and antimatter should have been created in equal amounts. When they meet, they annihilate each other, producing pure energy. If perfect symmetry had existed, the universe might have been left with nothing but radiation. Yet something caused a tiny imbalance, leaving behind a small fraction of matter that would go on to form everything we see today. This asymmetry is one of the great mysteries of physics. It suggests that during the early moments of the universe, certain processes favored the creation of matter over antimatter. Scientists are still searching for the exact mechanisms behind this imbalance, studying high-energy particle interactions and exploring theories that extend beyond the current understanding of physics. Whatever the cause, this slight difference had enormous consequences. It allowed matter to survive and eventually form stars, planets, and life. As time progressed, the universe entered a phase where protons and neutrons could begin to interact more meaningfully. However, the temperature was still too high for stable nuclei to form immediately. High-energy photons, particles of light, constantly broke apart any nuclei that attempted to form. It was only after the universe cooled further that these processes could proceed without being undone. Throughout this period, the universe remained a hot, dense plasma of particles and radiation. Photons dominated the energy content, scattering off charged particles and preventing light from traveling freely. The universe was opaque, meaning that it did not allow light to pass through without interaction. This opacity would persist for hundreds of thousands of years, creating a kind of cosmic fog that obscured the earliest structures. Despite this, important processes were already underway. Tiny fluctuations in density originating from the stretched quantum variations during inflation began to influence how matter was distributed. Regions that were slightly denser exerted a stronger gravitational pull, attracting more matter and becoming even denser over time. These variations were incredibly small, but they would eventually grow into the large-scale structures of the universe. The interplay between expansion and gravity defined the evolution of these fluctuations. While expansion worked to spread matter out, gravity pulled it together. The balance between these two forces determined how quickly structures could form and how large they could become. This delicate balance is one of the reasons the universe appears as it does today, with galaxies arranged in vast networks separated by enormous voids. Another key feature of the early universe was its remarkable uniformity. Measurements of the cosmic background radiation show that the temperature of the universe was almost the same in all directions, with only tiny variations. This uniformity is one of the strongest pieces of evidence supporting the idea of inflation. Without a rapid expansion in the early moments, it would be difficult to explain how distant regions of the universe, which appear not to have been in contact, could have such similar properties. As we look back at these first moments, it becomes clear that the universe was governed by a combination of simplicity and complexity. The laws of physics were consistent and predictable, yet the outcomes they produced were rich and varied. Small fluctuations led to large structures. Tiny imbalances led to the existence of matter. Rapid expansion created a vast and uniform cosmos. Each of these elements played a role in shaping the universe we observe today. The study of these early moments relies on both theoretical models and experimental evidence. Particle accelerators attempt to recreate conditions similar to those that existed shortly after the beginning, allowing scientists to study how particles behave at high energies. Observations of cosmic background radiation provide a snapshot of the universe at a later stage, offering clues about what came before. Together, these approaches help build a coherent picture of the universe's earliest history. Yet there are still gaps in our understanding. The exact nature of inflation, the origin of matter, antimatter, asymmetry, and the behavior of gravity at extremely high energies remain open questions. These mysteries drive ongoing research and inspire new theories. They remind us that while we have come a long way in understanding the universe, there is still much to discover. As the universe continued to expand and cool, it moved closer to a state where the first simple elements could form. The chaotic interactions of particles began to settle into more stable configurations. The stage was being set for the next major phase in cosmic history, where nuclei would combine and the first building blocks of atoms would emerge. These early moments, though brief, were incredibly important. They determined the composition of the universe, the distribution of matter, and the seeds of structure. Without them, the universe would not have evolved in the way it did. Every galaxy, every star, and every atom traces its origins back to this intense and dynamic period. In this chapter, we have explored a time when the universe was still taking shape, when the fundamental aspects of reality were being established. It is a time that challenges our imagination and pushes the limits of our understanding. Yet, it is also a time that connects us to the deepest origins of existence. By studying these first moments, we gain insight into how the universe transformed from a state of pure energy into the complex and structured cosmos we inhabit today. As the universe continued to expand and cool from its earliest, most violent beginnings, it entered a phase where chaos slowly gave way to structure. The extreme energies that once prevented stable formations began to drop, allowing the first meaningful steps toward matter as we recognize it today. This period marked a profound transition in cosmic history, where the raw ingredients of the universe began assembling into more complex forms. It was no longer just a turbulent sea of particles appearing and disappearing, but a place where stability could finally emerge. In the first few minutes after the beginning, conditions became just right for a critical process known as Big Bang nucleosynthesis. During this time, protons and neutrons, which had already formed from earlier particle interactions, began to combine into the nuclei of the lightest elements. This was not a slow or gentle process. It occurred rapidly within a narrow window when the temperature and density of the universe allowed nuclear reactions to take place without being instantly undone by high-energy radiation. The most abundant product of this phase was hydrogen, the simplest element consisting of a single proton. Alongside hydrogen, helium nuclei also formed in significant quantities, made up of 2 protons and 2 neutrons. Smaller amounts of deuterium, a heavier form of hydrogen, and traces of lithium were also created. These elements became the foundation for everything that followed. Nearly all the ordinary matter in the universe today can trace its origins back to this brief but crucial period. What is remarkable about this process is how precisely it aligns with what we observe today. When scientists measure the abundance of hydrogen and helium in distant regions of the universe, they find proportions that closely match predictions from nucleosynthesis models. This agreement is one of the strongest pieces of evidence supporting our understanding of the early universe. It shows that even in its infancy, the cosmos followed consistent and predictable physical laws. Despite the formation of atomic nuclei, the universe was still far from forming atoms. The temperature remained extremely high and electrons moved freely, unable to bind with nuclei. Whenever an electron approached a nucleus, high-energy photons would immediately knock it away. The universe existed as a plasma, a state of matter where charged particles move independently rather than forming neutral atoms. This plasma filled all of space, creating a dense and opaque environment. Light during this period could not travel freely. Photons constantly interacted with electrons, scattering in all directions. This made the universe effectively opaque, similar to the interior of a star where light struggles to escape. If an observer had somehow existed at this time, they would not have seen stars or galaxies. There was only a glowing, uniform brightness, with no clear structures or shapes. As expansion continued, the temperature gradually dropped further. Over hundreds of thousands of years, the universe cooled enough for a major transition to occur. Electrons began to slow down and lose enough energy to be captured by atomic nuclei. This process is known as recombination, although it was actually the first time these particles combined. When electrons joined with protons, they formed neutral hydrogen atoms. Helium nuclei also captured electrons, forming neutral helium atoms. This transition had a dramatic effect on the universe. With electrons now bound into atoms, photons no longer scattered as frequently. Light could finally travel long distances without constant interruption. The universe, once opaque, became transparent. This moment marked the release of radiation that had been trapped since the early stages. That radiation still exists today as the cosmic microwave background, a faint glow that fills all of space and provides a snapshot of the universe at this exact moment. The cosmic microwave background is one of the most important discoveries in modern cosmology. It represents the oldest light we can observe, dating back to when the universe was about 380,000 years old. Although it appears nearly uniform, it contains tiny fluctuations in temperature. These variations correspond to slight differences in density, regions where matter was either slightly more concentrated or slightly less so. These small irregularities would eventually grow into the large-scale structures we see today, including galaxies and clusters of galaxies. At this stage, the universe entered a period often referred to as the cosmic dark ages. With atoms formed and light traveling freely, one might expect the universe to be bright and full of visible structures. However, no stars had formed yet. There were no sources of new light, only the fading glow of the background radiation. The universe was filled with vast clouds of hydrogen and helium gas, slowly evolving under the influence of gravity. Gravity now began to play a more dominant role. Regions with slightly higher density started to attract more matter, growing gradually over time. This process was slow but steady. As matter accumulated, these regions became denser and hotter, setting the stage for the eventual formation of stars. The seeds of structure, planted in the earliest moments of the universe, were beginning to take shape. Another invisible but crucial component was also influencing this process. Although it cannot be seen directly, dark matter provided additional gravitational pull. It helped guide the formation of structures by creating gravitational wells into which ordinary matter could fall. Without dark matter, the formation of galaxies would have been much slower and less efficient. Its presence shaped the large-scale architecture of the universe in fundamental ways. During the Dark Ages, the universe may have seemed quiet and uneventful, but beneath this calm surface, important changes were taking place. Gas clouds were gradually collapsing under gravity, heating up as they did so. Over time, these collapsing regions would become dense enough to ignite nuclear fusion, giving birth to the first stars. But before that could happen, the universe had to pass through this long period of darkness and gradual transformation. The story of this chapter is one of transition, from the formation of nuclei to the creation of atoms, from opacity to transparency, from uniformity to the beginnings of structure. Each step built upon the previous one, guided by the laws of physics and the conditions set in the earliest moments. It is a process that shows how complexity can emerge from simplicity over time. What makes this period especially fascinating is how much we can learn about it despite its distance in time. By studying the cosmic microwave background, scientists can map the tiny fluctuations that existed in the early universe. These maps reveal patterns that correspond to the seeds of galaxies, providing a direct link between the past and the present. It is like looking at a blueprint of the universe before its structures fully formed. The formation of the first atoms also had profound implications for the future. Neutral atoms interact differently with radiation compared to charged particles. This change allowed the universe to cool more efficiently and set the stage for the next phase of evolution. It also made it possible for matter to begin clumping together in more stable ways, leading to the eventual formation of stars and galaxies. As we follow this journey, it becomes clear that the universe is not static. It is constantly changing, evolving from one state to another. Each phase is connected to the next, forming a continuous chain of events that stretches from the beginning to the present day. The processes that occurred in these early stages determined the composition, structure, and behavior of the universe on the largest scales. There is also a sense of unity in this story. The same physical laws that govern the behavior of atoms on Earth also shaped the evolution of the entire cosmos. The interactions between particles in the early universe follow the same principles that we observe in laboratories today. This consistency allows scientists to test theories and build models that explain events billions of years in the past. Yet, even with all this knowledge, mysteries remain. The exact nature of dark matter is still unknown. The detailed processes that led from simple gas clouds to the first stars are still being studied. Each answer leads to new questions, pushing the boundaries of our understanding further. As the universe moved beyond this stage, the conditions became ripe for a dramatic transformation. The Dark Ages would eventually end with the ignition of the first stars, bringing light back into the cosmos and beginning a new chapter in its history. These stars would not only illuminate the universe but also create heavier elements, paving the way for planets and life. In this chapter, we have witnessed the universe taking its first steps towards structure and clarity. From a hot, opaque plasma to a transparent cosmos filled with neutral atoms, the transformation was both profound and essential. It set the stage for everything that followed, laying the groundwork for the formation of stars, galaxies, and ultimately the complex universe we observe today. After the universe became transparent and the first neutral atoms formed, a long and quiet era began. It was a time without stars, without galaxies, and without any visible sources of light beyond the faint afterglow left behind from earlier stages. This period is often called the Cosmic Dark Ages, and despite its name, it was one of the most important phases in the history of the universe. Beneath the apparent stillness, the foundations of cosmic structure were slowly taking shape. At this stage, the universe was filled almost entirely with hydrogen and helium gas. These elements, created during the early moments of cosmic evolution, drifted through space in vast, diffuse clouds. The temperature had dropped significantly compared to earlier times, allowing atoms to remain stable. The universe was no longer a chaotic plasma, but a calm, expanding environment where matter could begin to organize itself under the influence of gravity. Although the universe appeared uniform on large scales, it was not perfectly even. Tiny fluctuations in density, remnants of earlier processes, created regions that were slightly denser than their surroundings. These differences were incredibly small, often less than 1 part in 100,000. Yet they would determine the entire future structure of the cosmos. Gravity amplified these small variations over time, pulling matter into denser regions while leaving other areas more empty. The role of dark matter became especially significant during this period. Unlike ordinary matter, dark matter does not interact with light, making it invisible to direct observation. However, it exerts gravitational influence, and in the early universe, it began to form dense regions known as halos. These halos acted as gravitational anchors, drawing in surrounding gas and helping to accelerate the formation of larger structures. Ordinary matter, primarily hydrogen and helium, followed the gravitational pull of dark matter. Slowly, gas began to accumulate in these halos, increasing in density over millions of years. As gas fell inward, it also began to heat up due to compression. This heating process was crucial because it set the stage for the next major transformation in the universe. However, the process was not simple. Gas clouds had to cool efficiently in order to collapse further and form stars. Cooling mechanisms during this time were limited. With only hydrogen and helium present, there were fewer ways for gas to release energy. Yet, under the right conditions, hydrogen atoms could form molecules, and these molecules allowed the gas to radiate energy away more effectively. As the gas cooled, it could collapse further under gravity, becoming denser and hotter at its core. This gradual process took millions of years, but eventually it reached a critical point. In the densest regions of these gas clouds, pressure and temperature rose high enough to trigger nuclear fusion. This marked the birth of the first stars, often referred to as population 3 stars. These stars were very different from those we see today. Because they formed from pristine gas with almost no heavier elements, they were likely much more massive, hotter, and shorter-lived than modern stars. Some may have been hundreds of times more massive than the Sunday. The ignition of these first stars ended the cosmic dark ages. For the first time since the early universe became transparent, new sources of light appeared. These stars emitted intense radiation, illuminating their surroundings and transforming the environment around them. Their light began to break apart neutral hydrogen atoms, reionizing the gas and making the universe more transparent once again. This process is known as reionization, and it marked another major transition in cosmic history. The radiation from these early stars did more than just provide light. It also influenced the formation of future generations of stars. By heating and ionizing the surrounding gas, it could prevent some regions from collapsing while encouraging others to form new structures. This feedback effect created a complex interplay between star formation and the surrounding environment, shaping the evolution of galaxies. At the same time, these massive stars lived very short lives. Because of their size and high energy output, they burned through their nuclear fuel quickly, often in just a few million years. When they reached the end of their lives, they exploded in powerful supernovae. These explosions scattered newly formed elements into the surrounding space, enriching the gas with heavier elements such as carbon, oxygen, and iron. This enrichment was a turning point. The presence of heavier elements allowed gas to cool more efficiently, making it easier for smaller and more stable stars to form. Over time, this led to the creation of stars more similar to those we observe today. It also set the stage for the formation of planets, since heavier elements are essential for building solid structures. As more stars formed, they began to group together under the influence of gravity, forming the first galaxies. These early galaxies were much smaller and less organized than modern ones, but they represented the beginning of large-scale cosmic structure. Over time, galaxies would merge and grow, forming the vast systems we see in the universe today. The process of galaxy formation was not uniform. Some regions of the universe formed structures more quickly, while others remained relatively empty. This led to the development of a cosmic web, a vast network of filaments and voids where galaxies are distributed in a complex pattern. This structure is still visible today and provides important clues about the early universe. Throughout the cosmic dark ages and the emergence of the first stars, the universe was undergoing a gradual transformation from simplicity to complexity. What began as a nearly uniform distribution of gas evolved into a richly structured cosmos filled with light and motion. Each step in this process was driven by the interplay of fundamental forces, particularly gravity, which acted as the engine of structure formation. One of the most fascinating aspects of this period is how small initial differences led to enormous consequences. Tiny fluctuations in density grew into galaxies and clusters of galaxies. The slight imbalance between matter and antimatter allowed matter to dominate. The formation of the first stars introduced the elements necessary for life. These connections highlight the delicate balance that shaped the universe. Modern observations allow scientists to study this era in remarkable detail. Powerful telescopes can detect light from distant galaxies, showing us the universe as it was billions of years ago. By looking far enough into space, we can observe the end of the Dark Ages and the beginning of reionization. These observations provide valuable insights into how the first structures formed and how the universe evolved over time. Despite these advances, many questions remain. The exact properties of the first stars are still uncertain, as they have not been directly observed. The nature of dark matter continues to be a mystery, and its role in structure formation is still being explored. The details of reionization, including how quickly it occurred and which sources contributed most, are also active areas of research. What is clear, however, is that the cosmic dark ages were far from empty or unimportant. They were a period of quiet preparation, during which the universe laid the groundwork for everything that followed. Without this phase, there would be no stars, no galaxies, and no complex structures. It was a necessary step in the evolution of the cosmos. As the first stars lit up the universe, they began a chain reaction of creation and transformation. Light returned to the cosmos, and with it came new possibilities. The universe was no longer a dark, featureless expanse, but a dynamic environment filled with energy and activity. This marked the beginning of a new era, one in which the building blocks of galaxies and eventually life would take shape. In this chapter, we have explored a time of subtle but powerful change, from the formation of dark matter halos to the ignition of the first stars. The universe transitioned from darkness to light. It is a story of patience and gradual evolution, where small beginnings led to extraordinary outcomes. As we move forward, the focus shifts to the structures that emerged from this process, the galaxies that would become the homes of stars, planets, and ultimately observers capable of understanding the universe itself. As the first stars ignited and ended the long cosmic dark ages, the universe entered a period of transformation that would define its large-scale structure for billions of years. Light had returned, but this was not the gentle glow of later generations of stars. These early sources of light were intense, powerful, and short-lived. They reshaped their surroundings and triggered a chain reaction of formation, destruction, and rebirth that would eventually lead to the vast galaxies we observe today. The earliest stars, often referred to as population 3 stars, were unlike anything in the modern universe. Formed from pristine hydrogen and helium, they lacked the heavier elements that influence how stars evolve today. Without these elements, the gas clouds from which they formed cooled less efficiently, leading to the creation of stars that were much more massive than typical stars now. Some may have reached masses hundreds of times greater than the Sun, burning at extremely high temperatures and radiating enormous amounts of energy. These stars lived fast and died young. Their immense mass caused them to burn through nuclear fuel at a rapid pace, often lasting only a few million years. In cosmic terms, this is a brief existence. Yet, despite their short lives, they played a critical role in shaping the universe. Through nuclear fusion, they created the first heavy elements that did not exist in the universe before their formation. Carbon, oxygen, and other building blocks of future planets and life were forged in their cores. When these massive stars reached the end of their lives, many exploded in violent supernovae. These explosions were among the most energetic events in the early universe. They released vast amounts of energy and scattered newly formed elements into the surrounding space. This process enriched the interstellar medium, changing its composition and allowing for new types of stars to form. The universe was no longer made solely of hydrogen and helium. It now contained the ingredients necessary for more complex structures. At the same time, the radiation from these stars began to transform the universe on a larger scale. Their intense ultraviolet light ionized the surrounding hydrogen gas, breaking atoms back into protons and electrons. This process, known as reionization, gradually spread across the universe. Regions around early stars and galaxies became ionized bubbles, which grew and merged over time. Eventually, much of the universe became ionized, marking a major phase transition in its evolution. While stars were forming and evolving, gravity was organizing matter on even larger scales. Small clusters of stars began to group together, forming the earliest galaxies. These primitive galaxies were not the well-defined spirals or ellipticals we see today. They were irregular and chaotic, shaped by constant interactions and mergers. Over time, gravity pulled these systems together, causing them to grow larger and more complex. The formation of galaxies was closely linked to the presence of dark matter. Dark matter provided the underlying scaffolding for galaxy formation. Its gravitational influence created deep wells into which gas could fall. Without dark matter, the formation of galaxies would have been far slower and less efficient. It played a silent but essential role, guiding the distribution of matter across the universe. As gas accumulated in these dark matter halos, it cooled and condensed, forming new generations of stars. Unlike the first stars, these later stars contained heavier elements, which allowed them to form in a wider range of sizes. This marked the transition from population 3 stars to population 2 stars, and eventually to population 1 stars, like our Sun. Each generation of stars contributed to the enrichment of the universe, increasing the abundance of heavy elements over time. Galaxies did not form in isolation. They existed within a vast network known as the cosmic web, a structure composed of filaments, nodes, and voids. Matter was not evenly distributed, but instead concentrated along these filaments, where galaxies and clusters formed. Large empty regions, known as voids, contained relatively little matter. This web-like structure emerged from the tiny fluctuations present in the early universe, amplified over billions of years by gravity. Collisions and mergers between galaxies became common as the universe evolved. When galaxies interacted, their shapes were distorted and their stars were redistributed. Gas within these galaxies could be compressed during collisions, triggering bursts of star formation. These events played a key role in shaping the diversity of galaxies we observe today. Some galaxies grew into massive elliptical systems, while others developed rotating disks and spiral arms. At the centers of many galaxies, another phenomenon began to emerge. Supermassive black holes formed and grew, possibly from the remnants of the earliest massive stars or from the direct collapse of dense gas clouds. These black holes could contain millions or even billions of times the mass of the Sunday. As matter fell into them, it released enormous amounts of energy, sometimes outshining the entire galaxy. These active galactic nuclei influenced their surroundings, regulating star formation and shaping the evolution of galaxies. The interplay between star formation, supernova explosions, and black hole activity created a dynamic and ever-changing environment. Energy and matter were constantly being exchanged between stars, gas, and the surrounding space. This cycle of creation and destruction drove the evolution of galaxies, leading to increasingly complex structures. As billions of years passed, galaxies continued to grow and evolve. Smaller galaxies merged to form larger ones, and clusters of galaxies formed under the influence of gravity. These clusters became some of the largest structures in the universe, containing hundreds or even thousands of galaxies bound together. The universe, once nearly uniform, had transformed into a rich and varied landscape of structures. One of the most remarkable aspects of this process is how it connects the smallest and largest scales. The behavior of individual atoms influenced the formation of stars, which in turn shaped galaxies, which then formed clusters and superclusters. Each level of structure built upon the previous one, creating a hierarchy that spans an enormous range of scales. Observations of distant galaxies allow scientists to study this evolution in detail. Because light takes time to travel, looking at distant objects means looking back in time. By observing galaxies at different distances, scientists can piece together a timeline of how galaxies formed and evolved. This has revealed a universe that was once filled with smaller, more irregular galaxies, gradually evolving into the larger and more structured systems we see today. Despite the progress in understanding galaxy formation, many questions remain. The exact processes that led to the formation of the first galaxies are still being studied. The role of feedback from stars and black holes in regulating star formation is complex and not fully understood. The nature of dark matter continues to be one of the biggest mysteries in physics, influencing every stage of cosmic evolution. What is clear is that this period marked a turning point in the history of the universe. It was the era when the first stable structures formed, when light from stars began to dominate, and when the universe started to take on a recognizable shape. The transition from a simple, nearly uniform state to a complex, structured cosmos was one of the most profound changes in its history. As galaxies formed and evolved, they created the environments where future stars and planetary systems would emerge. The heavy elements produced in earlier generations of stars became the building blocks for planets, moons, and eventually life. The processes that began in this era set the stage for everything that followed, including the formation of our own galaxy and solar system. In this chapter, we have explored the rise of stars and galaxies, the transformation of the universe through light and structure, and the forces that shaped these developments. It is a story of growth and complexity, driven by gravity and fueled by the energy of stars. The universe, once dark and simple, had become a vibrant and dynamic place, filled with light and structure. As we move forward, the focus shifts to the elements created within stars and how they spread across the universe. These elements would play a crucial role in the formation of planets and the emergence of life, linking the cosmic story to our own existence in a deeply meaningful way. As galaxies grew in size and complexity, and generations of stars lived and died across the cosmos, the universe entered a phase where the creation of elements became one of the most important processes shaping everything that followed. In the earliest times, the universe contained only the simplest elements, mainly hydrogen and helium, formed during the first minutes after the beginning. But the universe we see today is rich with a wide variety of elements, from carbon and oxygen to iron and gold. These elements did not exist at the start. They were forged inside stars through processes that transformed simple matter into the building blocks of planets, life, and even the human body. The story of these elements begins in the hearts of stars. Stars are not just sources of light and heat, they are vast nuclear furnaces where atoms are constantly being transformed. At the core of a star, extreme pressure and temperature allow hydrogen nuclei to fuse together, forming helium. This process releases enormous amounts of energy, which is what makes stars shine. For most of a star's life, this fusion of hydrogen into helium is the primary source of its energy. As a star exhausts its hydrogen fuel, its internal structure begins to change. The core contracts under gravity, causing temperatures to rise even further. If the star is massive enough, these higher temperatures allow new types of fusion reactions to occur. Helium nuclei begin to fuse into heavier elements, such as carbon and oxygen. In even more massive stars, this process continues, creating elements like neon, magnesium, silicon, and eventually iron. Iron represents a turning point in the life of a star. Fusion reactions that produce elements lighter than iron release energy, helping to support the star against gravitational collapse. But creating elements heavier than iron requires energy rather than releasing it. This means that once a star's core becomes dominated by iron, it can no longer sustain the balance between outward pressure and inward gravity. The result is a dramatic and violent collapse. When this collapse occurs in a massive star, it leads to a powerful explosion known as a supernova. In a matter of seconds, the star's core collapses and rebounds, sending shock waves outward that tear the star apart. The energy released in a supernova is immense, briefly outshining entire galaxies. But beyond its dramatic appearance, a supernova plays a crucial role in the chemical evolution of the universe. During these explosions, conditions become extreme enough to create elements heavier than iron. Through rapid nuclear reactions, elements such as gold, uranium, and many others are formed. These elements are then scattered into space, enriching the surrounding gas with new material. This process is known as nucleosynthesis, and it is responsible for creating much of the diversity of elements found in the universe today. The cycle of star formation and destruction ensures that each new generation of stars forms from gas that is increasingly enriched with heavy elements. Early stars, made almost entirely of hydrogen and helium, produced the first heavy elements. Later stars formed from this enriched material, allowing for more complex chemistry and new possibilities. Over billions of years, this gradual buildup of elements transformed the universe from a simple environment into one capable of supporting planets and life. One of the most important elements created in stars is carbon. Carbon has unique properties that allow it to form complex molecules, making it the foundation of organic chemistry. Without carbon, life as we know it would not exist. Oxygen, another product of stellar fusion, is essential for water and for the respiration processes of many living organisms. Iron, produced in the cores of massive stars and distributed by supernovae, plays a critical role in planetary formation and even in the biology of living beings. In addition to supernovae, other processes also contribute to the creation of heavy elements. Collisions between neutron stars, the dense remnants of massive stars, can produce enormous amounts of heavy elements in a short time. These events, though rare, are believed to be responsible for much of the gold and other heavy elements in the universe. Such events show that even the most extreme and violent occurrences in the cosmos contribute to the building blocks of existence. As galaxies evolved, the distribution of these elements became more complex. Regions with active star formation became enriched more quickly, while other areas remained relatively primitive. This variation in chemical composition influenced the types of stars and planetary systems that could form. It also played a role in the development of galaxies themselves, affecting their structure and evolution over time. Our own galaxy, the Milky Way, is a product of this long history of element formation and distribution. It contains stars of different ages and compositions, reflecting the ongoing process of cosmic evolution. Some stars are ancient and contain very few heavy elements, while others, like the Sun, formed later and are rich in the products of previous generations of stars. The presence of heavy elements allowed for the formation of solid particles within clouds of gas and dust. These particles could stick together, forming larger structures over time. This process would eventually lead to the formation of planets, moons, and other solid bodies. Without the elements created in stars, such structures would not be possible. The universe would consist only of gas, with no solid surfaces or complex chemistry. The connection between stars and life is one of the most profound insights in science. Every atom in the human body, except for hydrogen, was created in a star or during a supernova. The calcium in our bones, the iron in our blood, and the oxygen we breathe all have their origins in stellar processes. This means that in a very real sense, we are made of stardust. Our existence is directly linked to the life cycles of stars. This realization changes how we view our place in the universe. We are not separate from the cosmos, but a part of its ongoing evolution. The processes that began billions of years ago continue to shape the universe today. New stars are still forming, and old stars are still dying, continuing the cycle of creation and destruction that drives cosmic evolution. The study of element formation also provides important clues about the history of the universe. By analyzing the composition of stars and galaxies, scientists can determine their ages and trace their evolution. Different elements are produced in different types of stars and events, so their presence reveals information about the processes that occurred in the past. This makes the chemical composition of the universe a kind of record of its history. Despite the progress made in understanding these processes, there are still many unanswered questions. The exact details of how certain elements are formed, especially in extreme environments, are still being studied. The role of different types of supernovae and stellar collisions continues to be an active area of research. Each new discovery adds to our understanding of how the universe became chemically diverse. As the universe continued to evolve, the increasing abundance of heavy elements set the stage for a new level of complexity. Gas clouds enriched with these elements could cool more efficiently, leading to the formation of smaller and more stable stars. Around these stars, disks of gas and dust could form, eventually giving rise to planetary systems. This marked the beginning of a new chapter in cosmic history, one that would eventually lead to the formation of Earth and the emergence of life. In this chapter, we have explored how the elements that make up the universe were created and distributed. From the fusion processes inside stars to the explosive power of supernovae, these events transformed simple matter into the building blocks of everything we see around us. It is a story of transformation and connection, linking the life cycles of stars to the existence of planets and living beings. The universe, once composed of only the simplest elements, had become a chemically rich environment capable of supporting incredible complexity. This transformation did not happen all at once, but gradually, over billions of years, through countless generations of stars. Each generation added to the richness of the cosmos, bringing it closer to the conditions necessary for life. As we move forward, the focus shifts to how these elements came together to form planetary systems, including our own. The processes that began in the hearts of stars would now shape the formation of worlds, setting the stage for one of the most remarkable developments in the history of the universe. As the universe matured and became enriched with heavier elements produced by countless generations of stars, a new level of structure began to emerge. The vast clouds of gas and dust that drifted through galaxies were no longer composed only of simple hydrogen and helium. They now contained carbon, oxygen, silicon, iron, and many other elements forged in stellar cores and scattered across space by supernova explosions. These enriched clouds became the birthplaces of something entirely new in the cosmic story. They became the origins of planetary systems. Within galaxies like the Milky Way, regions of dense gas and dust continued to collapse under the influence of gravity. These regions, known as molecular clouds, were cold and massive, sometimes spanning dozens or even hundreds of light years. Inside them, gravity slowly pulled material together, forming denser clumps that would eventually give rise to new stars. But unlike the earliest stars in the universe, these later generations formed in environments rich with heavy elements, allowing for a much more complex process to unfold. As a cloud of gas collapsed, it began to spin. This rotation was not something added from outside, but a natural result of tiny initial motions within the cloud. As the cloud shrank, its rotation increased, much like a spinning figure skater pulling in their arms. Over time, this spinning motion caused the collapsing material to flatten into a disk around a central forming star. This structure is known as a protoplanetary disk, and it is within this disk that planets begin to take shape. At the center of this disk, pressure and temperature rose as more material accumulated. Eventually, conditions became extreme enough to ignite nuclear fusion, marking the birth of a new star. In our case, this star would become the Sun, the central anchor of the solar system. Around it, the remaining material in the disk continued to orbit, setting the stage for the formation of planets, moons, asteroids, and comets. Inside the protoplanetary disk, dust grains began to collide and stick together. These tiny particles, composed of elements like silicon, carbon, and iron, formed the building blocks of larger structures. Through a process known as accretion, these particles gradually grew into larger clumps, eventually forming kilometer-sized bodies called planetesimals. This process was not smooth or orderly. Collisions were frequent, and not all of them led to growth. Some collisions shattered objects, creating debris that would later recombine in different ways. Over time, gravity began to dominate the process. Larger planetesimals attracted more material, growing rapidly and clearing their orbits. These growing bodies became protoplanets, the early stages of full-size planets. In the inner regions of the disk, where temperatures were higher, lighter elements like hydrogen and helium could not remain bound to forming planets. This led to the creation of rocky planets made primarily of heavier elements. In the outer regions, where temperatures were lower, gas could accumulate more easily, leading to the formation of gas giants. The formation of the solar system followed this general pattern. Close to the Sun, rocky planets like Mercury, Venus, Earth, and Mars took shape. Farther out, massive planets like Jupiter and Saturn formed, gathering large amounts of gas around solid cores. Even farther away, icy bodies and smaller objects populated the outer reaches, forming regions like the Kuiper Belt and the distant Oort cloud. During this period, the early solar system was a violent place. Collisions between forming bodies were common, and these impacts played a major role in shaping the planets. One of the most significant events in Earth's history likely occurred during this time, when a Mars-sized object collided with the young Earth. The debris from this impact eventually formed the Moon, creating a stable companion that would influence Earth's tides and rotation. As planets formed and evolved, their internal structures began to develop. Heat from collisions, radioactive decay, and gravitational compression caused many young planets to melt internally. This allowed heavier elements like iron to sink toward the center, forming dense cores, while lighter materials rose to form mantles and crusts. This process, known as differentiation, gave planets layered structures that would influence their geology and evolution. The presence of heavy elements also allowed for the formation of atmospheres. Volcanic activity released gases trapped within planetary interiors, creating early atmospheres composed of water vapor, carbon dioxide, nitrogen, and other compounds. In some cases, these atmospheres would evolve over time, influenced by factors such as solar radiation, planetary gravity, and chemical reactions. Water, one of the most important ingredients for life, became available through multiple processes. Some of it may have been present in the original disk, while additional amounts were delivered by icy bodies like comets and asteroids. On Earth, water accumulated on the surface, eventually forming oceans. These oceans would become the setting for one of the most remarkable developments in the universe, the emergence of life. The formation of planetary systems was not unique to our own. Observations of distant stars have revealed that planets are common throughout the galaxy. Thousands of exoplanets have been discovered, showing a wide variety of sizes, compositions, and orbital patterns. Some systems are very different from our own, with giant planets orbiting close to their stars or planets in highly eccentric orbits. This diversity highlights the range of possibilities that can arise from the same basic processes. Despite this diversity, the underlying principles remain the same. Gravity pulls matter together, rotation shapes the structure of disks, and collisions drive the growth of planets. The presence of heavy elements allows for the formation of solid bodies, while gas dynamics influence the development of atmospheres and larger planets. These processes, governed by the laws of physics, operate across the universe, creating planetary systems in countless locations. The formation of planets represents a major step in the evolution of the universe. It marks the transition from purely cosmic structures like stars and galaxies to environments where complex chemistry and potentially life can develop. Planets provide stable surfaces, varied environments, and the conditions necessary for long-term processes to unfold. They are the bridge between the large-scale universe and the emergence of living systems. Our own solar system is a product of billions of years of cosmic evolution. The elements that make up Earth were formed in ancient stars and scattered across space long before the Sun was born. These elements came together in a rotating disk, forming a planet that would eventually host life. This connection between the life cycles of stars and the formation of planets highlights the continuity of the cosmic story. As we study the solar system and other planetary systems, we gain insight into how common or rare these processes might be. The discovery of Earth-like planets in the habitable zones of other stars suggests that the conditions for life may exist elsewhere in the universe. While we have not yet found definitive evidence of life beyond Earth, the building blocks and environments appear to be widespread. The journey from a cloud of gas and dust to a fully formed planetary system is long and complex. It involves countless interactions, from microscopic collisions between dust grains to massive impacts between protoplanets. Each step is influenced by the conditions of the surrounding environment, the composition of the material, and the forces at play. Yet despite this complexity, the outcome is a system of remarkable order and structure. In this chapter, we have explored how the enriched universe gave rise to planetary systems, including our own. From the collapse of molecular clouds to the formation of protoplanetary disks and the growth of planets, each stage builds upon the previous one. It is a story of gradual assembly, shaped by gravity, motion, and the properties of matter. The formation of planets brings the cosmic narrative closer to something familiar. It is no longer just about distant galaxies and stars, but about worlds, environments, and the potential for life. It is a step that connects the vast scale of the universe to the smaller scale of human experience. As the universe continues to evolve, planetary systems remain dynamic. Collisions, migrations, and interactions continue to shape them long after their initial formation. Even today, our solar system is not completely static. Asteroids move through space, comets travel in long orbits, and planets continue their steady paths around the Sunday. The stage is now set for the next part of the story, the development of conditions that allow life to emerge and evolve. The processes that began with the birth of the universe have led, step by step, to the formation of a planet capable of supporting complex systems. It is a journey that spans billions of years, connecting the origins of the cosmos to the existence of life itself. As the solar system settled into a more stable configuration, a small, rocky planet orbiting an ordinary star began to undergo a series of transformations that would make it unlike any other world we know. That planet is Earth. Its story is not just one of formation, but of continuous change, shaped by internal forces, external impacts, and delicate balances that allowed something extraordinary to emerge. Out of a once molten surface and a hostile environment, conditions gradually developed that would allow life to begin and evolve over billions of years. In its earliest stage, Earth was a violent and unstable world. Formed from the collisions of countless planetesimals, it was intensely hot, with much of its surface covered in molten rock. Heavy elements like iron sank toward the center, forming a dense core, while lighter materials rose to create the mantle and crust. This process, known as differentiation, gave Earth its layered structure, which continues to influence its geology and magnetic field today. Frequent impacts from asteroids and comets added to the chaos of early Earth. These collisions released enormous amounts of energy, reshaping the surface and contributing additional material. Some of these incoming bodies likely carried water and organic compounds, delivering essential ingredients for future development. Over time, as the rate of impacts decreased, the planet began to cool. A solid crust formed, and volcanic activity released gases trapped within the interior, creating an early atmosphere. This primitive atmosphere was very different from the one we breathe today. It contained little to no oxygen and was instead composed of gases such as carbon dioxide, nitrogen, and water vapor. As the planet continued to cool, water vapor condensed into liquid form, leading to the formation of oceans. These early oceans covered much of the planet's surface, creating a stable environment where chemical reactions could occur over long periods. Within these oceans, a complex process began. Simple molecules interacted in countless ways, driven by energy from the sun, volcanic activity, and possibly lightning. Over time, these interactions led to the formation of more complex molecules, including those capable of storing information and replicating themselves. This marked the beginning of life. Although the exact details of how life first emerged remain one of the greatest scientific mysteries. The earliest forms of life were likely simple, single-celled organisms. These microscopic entities lived in the oceans, drawing energy from their surroundings. Some may have relied on chemical reactions near hydrothermal vents, while others harnessed sunlight through primitive forms of photosynthesis. These early life forms were small, but their impact on the planet would be enormous. One of the most significant developments in the history of life was the evolution of photosynthesis. Certain organisms developed the ability to use sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. Over millions of years, this process gradually increased the amount of oxygen in the atmosphere. At first, this oxygen reacted with elements in the oceans and the crust, but eventually it began to accumulate in the air. This rise in oxygen led to a major transformation known as the Great Oxygenation Event. For many existing organisms, oxygen was toxic, leading to widespread extinctions. But it also created new opportunities. Oxygen allowed for more efficient energy production within cells, paving the way for more complex life forms. It also led to the formation of the ozone layer, which protects the surface from harmful ultraviolet radiation. As oxygen levels increased, life continued to evolve. Cells became more complex, developing internal structures and specialized functions. Eventually, multicellular organisms emerged, marking a new level of biological organization. These organisms could grow larger and develop specialized tissues, leading to a wide variety of forms and functions. Over hundreds of millions of years, life diversified into countless species, adapting to different environments and conditions. The oceans filled with a variety of organisms, from simple algae to more complex animals. Eventually, life began to move onto land, leading to the development of plants, insects, and later, larger animals. Each step in this process built upon earlier developments, creating an intricate web of life. Throughout this time, Earth itself continued to change. The movement of tectonic plates reshaped continents, creating mountains, oceans, and changing climates. Volcanic activity and impacts continued to influence the environment. Climate shifts, including ice ages and warming periods, created challenges that life had to adapt to or face extinction. Mass extinction events played a significant role in shaping the course of evolution. These events, caused by factors such as volcanic eruptions, climate changes, or asteroid impacts, led to the disappearance of many species. However, they also opened up ecological niches, allowing new forms of life to evolve and diversify. One of the most well-known of these events led to the extinction of the dinosaurs, paving the way for mammals to become dominant. Among these mammals, one lineage eventually gave rise to humans. Over millions of years, evolutionary processes shaped our ancestors, leading to the development of larger brains, complex social behaviors, and the ability to use tools. Humans are a relatively recent addition to Earth's history, yet they have developed the capacity to observe and understand the universe in ways no other species has. What makes this story remarkable is how it connects the smallest scales of chemistry to the largest scales of the cosmos. The elements that make up living organisms were formed in ancient stars. The processes that govern chemical reactions are rooted in the same physical laws that shaped the universe from its beginning. Life is not separate from the cosmos, but a continuation of its evolution. Earth's position in the solar system also played a crucial role. Located in the habitable zone, it receives just the right amount of energy from the sun to allow liquid water to exist on its surface. Its size and composition allow it to retain an atmosphere and maintain geological activity. The presence of a magnetic field protects it from harmful solar radiation. Each of these factors contributes to making Earth a suitable environment for life. Despite this, Earth is not a static world. It continues to evolve, influenced by both internal processes and external forces. Human activity has also become a significant factor, altering the environment in ways that were not possible before. Understanding Earth's history provides insight into how delicate the balance of conditions for life can be. The search for life beyond Earth is a natural extension of this understanding. If the processes that led to life on Earth are common, then life may exist elsewhere in the universe. Scientists are studying other planets and moons within our solar system, as well as distant exoplanets, looking for signs of habitability and potential biological activity. While no definitive evidence has been found yet, the discovery of organic molecules and potentially habitable environments suggests that the conditions for life may not be unique. The story of Earth and life is still unfolding. Evolution continues, and new species emerge while others disappear. The environment changes, sometimes gradually and sometimes rapidly. The future of life on Earth will depend on many factors, including natural processes and human actions. In this chapter, we have explored how a once lifeless planet became a world filled with living organisms. From molten beginnings to the development of oceans, from simple molecules to complex life forms, each step represents a remarkable transformation. It is a story of resilience, adaptation, and continuous change. The emergence of life is one of the most profound developments in the history of the universe. It represents a level of complexity and organization that goes beyond physical structures. It introduces processes such as reproduction, evolution, and consciousness. Through life, the universe gains the ability to observe itself, to ask questions, and to seek understanding. As we move to the final chapter, the focus shifts to the present and the future. The universe continues to expand, and its fate remains uncertain. The same processes that shaped the past will influence what lies ahead. By understanding the journey from the beginning to the present, we gain insight into where the universe might be heading and what role we may play in that ongoing story. From the first moment of expansion to the formation of stars, galaxies, planets, and eventually life, The universe has followed a path of continuous transformation. What began as an unimaginably hot and dense state has evolved into a vast and structured cosmos filled with light, matter, and complexity. Yet even now, this story is far from complete. The universe continues to change, and its future remains one of the greatest questions in science. Today, we live in a universe that is expanding. Distant galaxies are moving away from each other as space itself stretches. This discovery, made in the early 20th century, fundamentally changed our understanding of the cosmos. It showed that the universe is not static, but dynamic. The expansion is not happening within space, but of space itself. Every region of the universe is being carried apart by this ongoing growth. This expansion was first inferred from observations of distant galaxies and their redshift, the stretching of light toward longer wavelengths as objects move away. Later measurements revealed that this expansion is not slowing down, as once expected, but is actually accelerating. This surprising discovery led to the idea that a mysterious form of energy, known as dark energy, may be driving this acceleration. Although its nature is still unknown, it appears to make up a large portion of the total energy content of the universe. The large-scale structure of the universe today is the result of billions of years of evolution. Galaxies are not randomly scattered, but arranged in a vast cosmic web. Filaments of matter stretch across enormous distances, connecting clusters of galaxies, while huge voids separate these structures. This pattern reflects the influence of gravity acting on tiny fluctuations that existed in the early universe. Over time, these small differences were amplified, shaping the universe we observe today. Within this cosmic structure, galaxies continue to evolve. Some collide and merge, forming larger systems. Others slowly run out of gas, reducing their rate of star formation. Stars within galaxies are born, live, and die, contributing to the ongoing cycle of matter. New generations of stars form from enriched material, continuing the process that began with the first stellar objects billions of years ago. Our own galaxy, the Milky Way, is part of this ongoing evolution. It contains hundreds of billions of stars, along with vast clouds of gas and dust. At its center lies a supermassive black hole, which influences the motion of surrounding stars and gas. The Milky Way is also on a collision course with another galaxy, Andromeda. In several billion years, these two galaxies will merge, forming a new, larger galaxy. The solar system, including Earth, continues to orbit within the Milky Way. The Sun itself is a middle-aged star, steadily converting hydrogen into helium in its core. It has been shining for about 4.5 billion years, and will continue to do so for several billion more. Eventually, it will exhaust its fuel, expand into a red giant, and shed its outer layers, leaving behind a dense remnant known as a white dwarf. This process will mark the end of the Sun's active life, but it will also contribute to the recycling of matter within the galaxy. While stars and galaxies evolve, the universe as a whole is also moving toward a distant future. If the current trend of accelerated expansion continues, galaxies outside our local group will eventually move beyond our observable horizon. Over extremely long timescales, the universe may become increasingly isolated, with fewer interactions between distant structures. Star formation will gradually decline as gas reservoirs are depleted. In such a future scenario, the universe may become dominated by long-lived stars, stellar remnants, and black holes. New stars will form less frequently, and existing ones will slowly burn out. Black holes. Some of the most stable objects in the universe may eventually dominate the cosmic landscape. Even they are not eternal, as theoretical processes such as Hawking radiation suggest. They may slowly evaporate over unimaginable timescales. Despite these distant possibilities, the universe today is still active and evolving. New stars continue to form in dense regions of gas. Planetary systems are still being created. Galaxies still interact and transform. On cosmic scales, the present moment is a dynamic and vibrant phase in the history of the universe. One of the most remarkable aspects of this cosmic story is the emergence of life on at least one known planet. On Earth, the same physical laws that govern galaxies and stars have given rise to chemistry, biology, and consciousness. Life is a natural consequence of the universe's evolution, emerging from the gradual increase in complexity over billions of years. Human beings, as part of this process, have developed the ability to observe and understand the universe. Through science and technology, we have uncovered the history of cosmic evolution, from the earliest moments of expansion to the formation of galaxies and planets. We have learned that the elements in our bodies were forged in stars, and that our existence is deeply connected to the history of the cosmos. The study of the universe is not only about understanding distant objects, but also about understanding ourselves. By looking outward, we also look inward, exploring our origins and our place in the vast structure of reality. Every discovery reveals a deeper connection between the smallest scales of matter and the largest scales of the universe. Modern observations continue to expand our knowledge. Powerful telescopes allow us to see galaxies billions of light years away, showing us the universe as it was in its early stages. Measurements of the cosmic microwave background provide insights into the conditions of the early universe. Studies of exoplanets reveal that planetary systems are common, suggesting that the ingredients for life may exist throughout the cosmos. Despite these advances, many fundamental questions remain unanswered. The true nature of dark matter and dark energy is still unknown. The exact conditions of the earliest moments of the universe are still being studied. The possibility of other universes beyond our own observable region remains a topic of theoretical exploration. Each answer we find leads to new questions, pushing the boundaries of knowledge further. The future of the universe is not just a scientific question, but also a philosophical one. It raises questions about meaning, existence, and the role of observers within a vast and evolving cosmos. If the universe continues to expand and change indefinitely, what does that mean for the structures and systems within it? How does life fit into this long-term evolution? These are questions that connect science with deeper reflection. What we do know is that the universe operates according to consistent laws that apply across space and time. The same principles that govern the motion of galaxies also govern the behavior of atoms. This Unity suggests that the universe is not a collection of unrelated parts, but a single interconnected system. Understanding one part helps us understand the whole. As we look toward the future, both near and distant, we see a universe that is still unfolding. Stars will continue to form and die. Galaxies will evolve and merge. Planets will change over time. Life, at least on Earth, will continue to adapt to changing conditions. The cosmic story is still being written. In this final chapter, we bring together the entire journey of the universe. From the initial expansion of space, through the formation of particles, atoms, stars, galaxies, planets, and life, to the present moment of observation and understanding. Each stage is connected, forming a continuous chain of events that spans billions of years. The universe began in a state of simplicity and has evolved into a state of immense complexity. Along the way, it has produced structures of incredible scale and diversity, from the smallest particles to the largest cosmic filaments. It has created environments where life can exist and observers can arise to study its history. We are part of this ongoing process. Our existence is tied to the evolution of the cosmos, and our understanding of it is one of its most remarkable outcomes. The universe is not separate from us. It is the environment from which we emerged, and the system within which we continue to exist. The story of the universe is not finished. It continues with every passing moment. New discoveries will expand our understanding, and new questions will emerge. The journey from the first light to the present is only one chapter in a much larger narrative that may continue far into the future. In the end, the universe is both the subject of our study and the source of our existence. It is vast beyond imagination, yet connected to us in fundamental ways. By exploring its history, we come closer to understanding not only where everything came from, but also what it means to be part of this extraordinary cosmic journey.